Let's prove the third Sylow theorem. So this is the last of the Sylow theorems, part 3. It says the following, that the number of distinct p Sylow subgroups of a group G, of a finite group G, is congruent to 1 modulo p. Okay, and the notation is more or less what we used in all the earlier theorems as well, earlier parts of the theorem, that we assume p divides the cardinality of the group. We write cardinality G as p to the d m. D is a power that's at least 1, and m of course is a number relatively prime to p, which again we assume is 1 or more. Okay, so let's prove the third Sylow theorem. Now this again involves some very interesting ideas, and as before it uses the set X that we have been looking at repeatedly. So here's the proof. So let's go back to the action of G on itself. So G acts on itself by just left translation. So recall we used both left and right translations in the earlier proof of Sylow 2. Now we'll go back to just the left translation. So G acts on itself by left translation, and therefore by the action on subsets, G acts on the set of all subsets of G of cardinality p power d, and we call this set X. And again, to recall, the key property of X was that it had a cardinality which was not divisible by p. And for this Sylow theorem 3, we will recall one additional fact about X. We actually knew a little bit more about the cardinality of X. Further, recall the cardinality of X was congruent to m modulo p. Okay, so this little fact has never been used in its full power until now. We've only used the fact that the cardinality of X is not divisible by p. We have never used the exact congruence modulo p that the cardinality satisfies. Okay, and since of course this particular statement here in Sylow 3 is a statement about something being congruent to something modulo p, it will turn out that this is exactly the fact that will play a role. Okay, so let's move on. So observe that this set X that we keep talking about is actually interesting for the following reason. So what is this set X really? So this set X, let's draw a picture of the set X. It's the set of all subsets. So what are elements of X? So it's X is nothing but all subsets of G whose cardinality is p power d. And so in particular, the p Sylow subgroups that we are looking at, the H or K that appeared in the earlier one. So any p Sylow subgroup, for example, is in fact an element of X. So let me give them names. So let's say that let's assume that the p Sylow subgroups are the following: H1, H2 till some number Hs be the distinct p Sylow subgroups. So recall, by the second Sylow theorem we know they're all conjugates of each other, be the distinct p Sylow subgroups of G. And so in fact they are all elements of this set X. So H1, this subgroup is somewhere in X. So maybe we'll just put them in different colors. So I have H2, another subgroup, and so on till I finally get my subgroup HS, just right here. So this is the last subgroup, H sub S. Okay, now H sub S. Okay, now here are some subsets of cardinality p power d, no doubt. Now let's do the following. Let's ask the following question: since they are all elements of X after all, what do their orbits look like? So recall the set X is a G set. It's got an action of the group G, the action on subsets, right? So recall, what's the action? G acts on X. Again, worth recalling once more, G acting on a subset A is just GA as A runs over A. Just multiply every element of A on the left. So in particular, we can ask, well, look at these p Sylow subgroups and let's ask what are their orbits under this action. Okay, so take the p Sylow subgroup hi, for example, or let's start with h1. H1 is an element of X, it's a subset of cardinality p power d. So it's a valid question to ask what's the orbit of this point. This it's now just a single point in the set X. So what's its orbit under the group action? Well, by definition, this is just going to be all elements of the form GH1. Okay, so remember GH1 is this G dot A. So it's just G dot A H1 as G runs over G. This is what the orbit means. Okay, but G dot H1 is, well, what's that? It's just this set which is you multiply every element of H1 on the left by G. Okay, just left multiplication. So what is this? The subsets you get in this way are exactly the left cosets. In other words, these are just the left cosets of the set H1. Okay, so this is an first interesting fact here, that when I look at H1, its orbit under the group is just going to be its various left cosets. So let me just mark them here. So these are the various left cosets of H1. Okay, so various GH1s. So this is the orbit of H1. Okay, now let's move on to H2 now. So observe, H2 is not in this orbit. Okay, this H2 being a distinct p Sylow subgroup. So note that in the orbit of H1, what you have are H1 and its various cosets. Among these, so observe, a coset can never be a subgroup except for the identity coset, meaning the coset of the original subgroup itself. All the other guys are not subgroups, they are not closed under multiplication. So this guy is the only subgroup here, and since H2 is assumed to be different from H1, H2 can't live inside this orbit, right? The only subgroup among these cosets is the one that I have shaded, and so if at all H2 lives in this orbit, it has to equal that guy, but H2 is not equal to H1. Okay, so observe, H2 is not in the orbit of H1. So that's all I'm trying to say here. So observe, H2 is in a separate orbit. Okay, so look at orbit of H2. What's that? Well, by the same token, this is just a set of all left cosets of H2. And so on. So you keep going this way. So you observe that at every step, the orbit of, so these left cosets here, this is the orbit of H2 under the group action. Okay, and so on until you reach the very end, and the orbit of HS will just be its left cosets. So that's the last orbit. Okay, and these are all disjoint. I mean, they are all more or less by definition of orbits, they are all disjoint sets. So I've produced some number of elements of the set X. Okay, so let's write X separately here again. So X is my ambient set, okay, on which the action takes place. Okay, now so what have we done so far? We have produced some elements of X, or rather we have produced some orbits inside the set X. Now how many elements of X are accounted for in this way? Okay, in other words, how many elements are there in each orbit? What's the cardinality of each orbit? So observe, so and so on. So this holds all the way till orbit of the last guy is just going to give me the set of all left cosets of HS. Okay, now observe, we know how many left cosets there are of any subgroup, right? So observe that the cardinality of the orbit of any one of the HIs by definition is just the number of left cosets of HI, and that of course is the cardinality of the group divided by the cardinality of HI, which in this case is p power d m divided by p power d. So that's m exactly. Okay, this holds for all I equals 1 to s. Any one of the p Sylow subgroups, the orbit cardinalities are exactly m. Okay, so let's go back to our picture of X. So what does that mean? It means that there are m elements here. So the cardinality of this set is m, the cardinality of this set is m, the cardinality of the last every one of them is M. Okay, and there are S of them. So there are, how many total elements of X are accounted for in these orbits. There are MS elements that lie in these S orbits. Okay, now let's look at the other elements. Of course, this doesn't exhaust all the elements of X, because these are all very special subsets of cardinality p power d. These are either the p Sylow subgroups themselves or their left cosets. Okay, so these are some very, very special kinds of subsets of cardinality p power d. But of course, there will be lots of other random subsets, right? So there are many, many other subsets here of cardinality p power d in the group G. So of course, I have to look at all of them next. Okay, so let's look at any one such guy. So let me pick some not so special subset A, which is not of this form, and ask, so here is a subset of cardinality p power d. I can ask the same question: what is its orbit going to look like? Okay, again, a very, very interesting question. If I take a random element of cardinality, random subset of cardinality p power d, and ask what is its orbit under the action of the group. In other words, if I keep hitting it on the left by different group elements, it produces new subsets of cardinality p power d. What can I say about that orbit? How many new subsets will I produce, for example? These p Sylow guys are very nice and regular in the sense that we know exactly what you will get when you, what their orbit looks like. When you keep left multiplying these subgroups by elements of G, you just produce the different cosets. Okay, but if A is not a subgroup, for example, then it's not clear. It's somewhat trickier. It's not so easy to figure out what happens. Okay, so I want to now next try and understand what does the orbit of A look like. Okay, so what is A now? So let's pick. So I want to say now consider. Okay, so let's just note this fact down as well. The sum of the orbits of these HIs, orbit cardinalities for these guys, is M times S. Okay, so many elements are nice in some sense. Okay, so this is done. Now let's move on to the other orbits. Okay, next let's pick. Suppose A is an element of X. In other words, i.e., A is a subset of the group of cardinality p power d, and A is not in any of these orbits, and A is, so how should I write it? A does not belong to the orbits that we have already looked at. Okay, what does that mean? i.e., A is not a left coset of a p Sylow subgroup. Okay, this is now my assumption on A, that it's not a left coset of a p Sylow subgroup. Now under this assumption, I want to ask, what can I say about the cardinality of the orbit of A? Okay, and here's my claim. Here's an important observation. For all such A, the cardinality of the orbit is divisible by p. This is the important claim. Observe, this does not hold for the other nice orbits that we have already looked at. So the orbits that we have looked at, their cardinalities, what was the cardinality, was M, right? So these are the cardinalities of the p Sylow subgroups. So those guys have orbit cardinalities which are not divisible by p, because M is of course not divisible by p by assumption. But if you are not one of these nice orbits, any other orbit has cardinality which is a multiple of p. Okay, so that's our claim. Okay, so let's prove the claim first. So proof of claim. Well, as always, we will use the counting formula. If you want to understand how many elements there are in a given orbit, you will have to understand what the stabilizer looks like. Okay, so let me just call this the stabilizer of A. Okay, so what is the stabilizer of A? So let me give that a name. So let L denote the stabilizer of A. It's a certain subgroup, remember, the stabilizer is always a subgroup. What is it? It's a set of all group elements which stabilize A. In other words, when you hit it on the left, when you act it on A, you should get back A. Okay, so this is the definition of the stabilizer. All those elements of the group such that you take A, you hit it on the left by G, you still get back the same set A. Of course, it can permute the elements of amongst A, but you should just get back the set A again. It should not take an element of A and move it to an element that's outside A. Okay, so this is the property of the, this is the definition of the stabilizer. So let's try and understand what the relationship is between A and its stabilizer. Okay, so let me draw the set A now. So maybe I will draw it the way I did in the inside the set X. So suppose my set A looks like this, like a diamond. So let's say this is my set A. Okay, now let's do the following. Let's pick an element A in A. So let's pick an element first in A. Okay, so take some element. So I've taken some element A. Now look at this stabilizer. So what is the stabilizer? The stabilizer is a certain subgroup with this property. Okay. Now observe, if I take an element, so consider the right coset LA. Okay, L is a subgroup, A is an element. I can look at the right coset LA. What is this? This is just all elements of the form LA, where L comes from L. Okay, but observe that L multiplied by A. So according to this formula, if I take an element of A, according to this definition, if I take an element of A and multiplied by an element from the stabilizer, the answer should again be inside A. So observe that every element of the form LA must again be inside A by definition of the stabilizer. Okay, so what does that mean? I take A, and if I look at this left coset LA, well, that entire thing is a subset of A. So as soon as an element belongs to A, its entire right coset of L belongs to A. Okay, so this entire thing is there. Okay, now we keep going. Suppose this exhausts A, then we are done. If not, there is another element inside A. Okay, so maybe we should call this A1. Pick an element A1 inside A. If LA1 is all of A, stop. Otherwise, look for an element A2 which is not in LA1, which is in A. Okay, apply the same reasoning. So pick A2 in A. So if LA1 is not the whole set A, pick A2 which is in A but not in LA1. And now again by the same reasoning, conclude that LA2 is also a subset of A. Okay, again by the definition of the stabilizer. So this entire coset LA2 is inside A, and so on. So you keep going that way till you observe that as soon as some element is there, its entire right coset is there. Okay, which means finally this process has to stop because everything is a finite set. And finally, when this process stops, what would you have obtained? You would have realized A as a union. A can therefore be written as a union of some right cosets of L, right? Some finitely many right cosets of L, they are all disjoint necessarily. That union of those many, some finitely many of them, should give you the set A. Okay, so this is just, we are just applying the definition of the stabilizer, okay, and the action on subsets. So what does that mean in particular? It says in particular this means that the cardinality of A has to equal cardinality of L times the number of right cosets which are contained, the number of right cosets which of L which are contained in A. In other words, this means that the cardinality of L, whatever it is, must divide the cardinality of A. Okay, because this is some number, of course. So it means that the left hand side is a multiple of the cardinality of L. Okay, but observe the cardinality of A was p power d to begin with. So what this means is therefore the cardinality of L must also be some power of a prime. It must look like some p power j, where j is a number between 0 and d. Okay, so we have concluded that the stabilizer is also a p group, but observe that, but the key point here is that L cannot have cardinality p power d, but observe that j cannot equal d. Okay, this maximum value is not allowed. Okay, why not? Because of the following reason: if j equals d, because if j equals d, then what that means is that L has cardinality p power d, which means if you look at the earlier, or look at this equation here, the cardinality of A is p power d, the cardinality of L is also p power d, which means that there should be exactly one right coset of L which is contained in A. Okay. So what that means is that, or if you look at this earlier picture, at the very first step, the very first right coset that you form, that already exhausts the entire set A, because the cardinality of that right coset is already p power d. Okay. So what this means is that A looks like this. It's just a single right coset, just LA1 alone will do the job. The very first one will do the job. Okay. So A is a single right coset, and L, remember, has cardinality p power d. So what does that mean? Well, it means L, of course, is therefore a p Sylow subgroup, and A is a right coset of a p Sylow subgroup. But observe that because of Sylow theorem number 2, here's something we can do. Let me rewrite this as follows: A1 inverse LA1. Okay, so I'll write this as A1 times this guy here is just a conjugate of L1, is a conjugate of L, so I will call this L dash maybe. Okay, so what is L dash? L dash is another subgroup whose cardinality is p power d. Okay, so what have I finally concluded? I have concluded that my set A is therefore a left coset of a p Sylow subgroup. Okay, so well, because all these p Sylow subgroups are, conjugate of a p Sylow subgroup is a p Sylow subgroup. So the right coset of a p Sylow subgroup is also the left coset of a different p Sylow subgroup. That's all we are saying here. Okay, now, but that, recall, is a contradiction, because we assumed to begin with that the set A was not, where was this assumption? We assumed that A is not a left coset of a p Sylow subgroup. It was such an A that we are looking at. So if J equals D, however, we conclude that A does look like that. A has to have that form. Okay, so this contradiction implies that our assumption was wrong. J has to be strictly smaller than D, can't equal D. But if J is strictly smaller than D, well, what does that mean? Cardinality of L is p power j, recall. So J is strictly smaller than D, therefore the orbit cardinality, the orbit of the set A that we looked at, its cardinality looks like cardinality G by the cardinality of the stabilizer, which is p to the d minus j, which is some strictly positive power of p. Okay, so this is divisible by p, because this d minus j is a strictly positive number. So p therefore divides the orbit cardinality. Okay, as required, as claimed. So this proves our claim. Okay, so let's take stock. Where are we now? We've gone back to let's go back to this picture that we drew right in the beginning. So we have this set X, we have these nice regular orbits, okay, which are the cosets of Sylow subgroups, and then we have sort of all these other irregular orbits. Now these orbits are orbits of other subsets A, which are not cosets of Sylow subgroups, and what we have just shown is that this orbit, the number of subsets that you get, so this orbit cardinality is divisible by p. So p divides the cardinality of this orbit. Okay, and the same holds for the other subsets as well. So if I pick some other arbitrary subset A which is not in this orbit, and I look at its orbit, how many other subsets are obtained by left translating this by G, that orbit again will have cardinality which is a multiple of p, and so on. Okay, Okay, so finally, where does this lead us? So now let's look at this big subset X and ask how many elements are there in X. So there are these two types of elements. On the one side, we said that these nice orbits, they account for ms elements, but the total size of X. So now let me compute the total size of X, which is these nice orbits and these not so nice orbits. So observe now the cardinality of X is, first it is ms, so these come from the nice orbits, left cosets of Sylow subgroups and so on, plus these other orbits. So these sum of cardinality of orbits OI, so let me just call it OI for now, where what is OI? OIs are these not so nice orbits, if you wish, whose cardinalities are divisible by p. So this is orbits of subsets A, which are not left cosets, of P Sylow subgroups. So these are the not so nice orbits, and so what this gives us is ms plus what we have here, we have just shown, is divisible by p, right? So this is a multiple of p. Each orbit here is has cardinality which looks like p times something. So the net answer is congruent. So this part is divisible by p, so I can ignore it when I am looking at congruence modulo p. So I conclude that the cardinality of X is therefore congruent to m times s modulo p, where s is the number of Sylow subgroups. Okay, but observe, we already know something, but we know, and this is the fact I recalled right in the beginning, that the cardinality of X by our other arguments is already congruent to m modulo p. Okay, so therefore we conclude that the number m and ms had better be congruent to each other modulo p, and well, we're almost there. You can observe, if you cancel the m from both sides, it implies that s is congruent to 1 mod p. Okay, and so that's the end of the proof. Just a little aside on this cancellation of m. So remember, I can cancel m because m is not congruent to 0 modulo p. Okay, if m is not divisible by p, I can cancel m from both sides of a congruence. And why is that? Because, so recall, what's given is this. I know I'm given that ms is congruent to m modulo p. This just means that their difference ms minus m is divisible by p. This is what a congruence means. But this means in particular that p divides m times s minus 1, and if p divides a product, but recall, when p divides a product but p doesn't divide one of the terms, right, this factor m has no powers of p in its prime factorization, then it means that p must divide the other term. That's the only way out. In other words, s must be congruent to 1 mod p. Okay, so this is just a little proof of why cancellation is valid. Okay, so again, so to broadly summarize the idea of the proof here, it again comes back to the very same thing as before. This action on cosets is what we study here. So the key point is really in understanding this figure here on this screen, which is when you look at all the subsets of X and you look at the left translation action on subsets, the Sylow subgroups and their cosets, they form a bunch of nice regular orbits. Okay, each orbit has cardinality m, and if there are s Sylow subgroups, the total number is ms. And then all the other orbits are the not so nice orbits, which are orbits of subsets A, which are not of this form, but those orbits all have cardinalities which are divisible by p. Okay, so all those orbits will be divisible by p, whereas each of these orbits are not divisible by p. Okay, and then that coupled with what we know about the cardinality of X completes the proof. Okay.